lecture is going to be about Bayesian reasoning. It's one of the many fundamental reasons why we are teaching in Data 101. One of this is that it's good to apply Bayesian reasoning in real life. We have countless examples of using it in real life, and I always call it optimist optimist theorem, because it turns bad numbers into much better sounding numbers, applying Bayesian reasoning. Another is that it's, of course, a foundation of pretty much anything in what later happened in data science, machine learning, statistics. It's the most fundamental, one of the most fundamental theorems in science. And it's kind of amazing, a little bit of a history, that it's 200 over 260 years, 250 years old, and the guy Thomas Bayes, who is attributed to this theorem, has been known only for this work. It was published after his death, and we'll get to that. But now let me first talk about what's fundamental, why it's so fundamental. First of all, it helps irrational pessimists. In other words, I would say Bayes' theorem, it is not as bad as you think it is. Better than anti-anxiety med. So, why is it the case? Because, you know, in the situations which are stressful, for example, you go to a doctor and you learn about negative or positive test, you learn bad news. There's a couple of questions which you have to ask before you really despair, and a lot of times the news is not as bad as you think, and we'll give this example later on. Therefore, it's very important to distinguish between so-called prior odds and posterior odds. Prior odds are a priori belief in what you're afraid of, let's say that you're sick. And posterior odds are odds after you learn results of a test. So before we delve into this, let's go to Bayesian reasoning and Bayes' theorem. So Bayes' sole publication during his lifetime was allegedly a mystical book entitled Divine Benevolence, where he we don't even know, by the way, whether he was an author of this book, where he kind of laid out the foundations of what is known today as Bayesian theorem. He was admitted to Royal Society of London in 1764, which is like a very prestigious scientific body. Today, you have to have hundreds and hundreds of papers and be a professor and published, etc. So just imagine that Thomas Bayes had no publications, had no books to his name, and somehow he was admitted to the Royal Society. So someone must have known how brilliant this man was. Today, it's unthinkable. His citation index, which is a measure of proficiency of a scientist, would be pathetic. So here he is. In 1742, he was elected a Fellow of Royal Society of London, and without publishing any scientific and mathematical work at that time. However, his work was published after his death, and eventually led to this very powerful concept of Bayesian reasoning, which we're going to discuss today. So this is very simple. There are three components of Bayesian reasoning: prior beliefs, observations, and posterior beliefs. So Bayesian theorem is about how observations change your beliefs, how they make your prior beliefs more likely or less likely. So in general, we have to identify two components of any statement which is kind of want to take on a Bayesian reasoning task, you know, There are two components of it, observation and belief. Observation is something we know, we observe. Belief, something we do not know. It's a probabilistic concept. Observation is not. Observation is something objective. We just measure the temperature. We just know that someone is a psychology major. That's an observation. The belief would be how likely it is, right, for a psychology major to get an A in my class, or how likely it is that you're sick after a positive test. For example, the belief is, or the worry is, I have COVID. Observation tested positive. So now, what does it mean? Does it mean I have COVID? Well, it all depends, right? It all depends on the properties of this test. Turns out it doesn't have to be the case. How? So this reaction, oh my God, I have COVID, may or may not be called for. So let's go to Bayesian reasoning. As I said, not so fast. Let's look at the quality of the test. And before we go to evaluation of the quality of the test, let's look at a table of odds and probabilities. We're gonna use the version of Bayesian theorem, which is called odds version of Bayesian theorem. That requires a bit of a very simple math, but converting probabilities to odds, right? So odds is something when you measure a given event and you measure a complement of the event. In other words, P and not P, and see what is the ratio. So it's P divided by 1 minus P, where P is a probability. Very simple. It's 1-to-1 correspondence. So probability 0.5 translates into 1-to-1 odds. Probability of 0.25 translates into 1-to-3 odds. And so on. You can see a probability of 0.01 translates into 1-to-99 odds. So we're going to use odds here, not probabilities. You can also easily translate odds back to the probability in a similar manner. So let's start with a prior. Prior is very important. We often forget about the prior, the base. How likely is to have COVID? Having my symptoms, I mean, let's say I have sneezing, I have a bit of a fever. So let's make some assumptions. Well, is it a 1 out of 10, 1 out of 100, 1 out of 1,000? All depends. I mean, the topic has been a little bit mute now, fortunately. 2 years ago, it would have been far more worrying. So let's assume it's 1 to 100. So 1% chance I have COVID, sneezing and having a temperature, right? So now I worry, I go and I take a test. And I test, let's assume I test positive, right? So now, do I have COVID or not? Well, it all depends, and that's what Bayes teaches us, what is so-called true positive rate and false positive rate. So true positive is if I have COVID, how likely the test will say yes? Better be close to 1, right? Better be very, very high, right? Catches COVID. So then false positive, which is absolutely critical. And that's the question which you always have to ask your doctor. What is a false positive of anything you take? COVID test, EKG, etc. Because false positives are the Achilles heel of tests. If I do not have COVID, how likely the test will scare me and say yes? So how many of those healthy people is going to capture and say yes? That ratio better be very, very low. So true positive better very, very high, close to 1. And false positive better be very, very low, close to 0. So let's take the COVID test, which we discuss here. Let's assume it's 99% true positive, which is pretty good. Let's also assume it's 1% false positive. In other words, it will scare me with positive result when I do not have COVID 1 in 100 times. Now, let's look at the numbers, right? So now we apply Bayesian theorem to calculate the odds, right? Posterior odds of having COVID. They're much better than you're saying. So we calculate true positive to false positive ratio. It's going to be 99, right? 0.99 divided by 0.01. Now we apply the Bayesian theorem odds formulation, which is very simple. We take prior odds and we multiply them by likelihood ratio, and we get posterior odds. So likelihood ratio is 99. It's pretty big. I mean, it's definitely more likely we have COVID now as we tested positive than it was before. Before the odds were 1 to 99, right? 1%. So it was 1 to 99 was my odds without taking the test. But now it's 99 times bigger. So what is it? 99 times 1 over 99 is 1. So, but that's not probability. That's not how I have COVID. It's 1 to 1. Okay? It's 1 to 1. So what does it mean? It means 50-50. Is that amazing? So you take this test, it sounds good, 99%, true positive, 1% false positive, but the odds are 50-50. I mean, you can walk out and say, you know, it's as good as tossing a coin. How do we compute prior odds, likelihood ratio, and posterior odds? Well, again, I mean, these are the formulas, right? So probability of belief, remember, that's why it's very important to identify belief and observation in your task, because it's going to change the entire calculation. If you make a mistake, you're going to calculate the wrong thing. So prior odds are calculated by taking probability of belief, dividing it by probability of not belief. That is probability of having COVID versus probability of not having COVID. Likelihood ratio is probability of observation happening under assumption that belief is true, divided by conditional probability of observation happening when belief is false. That's what we just defined. And posterior odds, finally, is the probability of the belief, having COVID in this case, conditional on observation divided by the complement of it. So that's kind of a posterior probabilities when we know the observation, when we know the test. So these are the notations. And this is COVID example continued. And as I said before, it's 99 times 1 over 99, 1 to 1. So 50-50. So that's why don't despair. Just ask, what is a true positive? What is a false positive? And true positive, they usually brag about, oh, it's virtually sure. It's never sure. It's never 1, but maybe it's going to be 99.9%. That's great. But ask about false positive, because if the false positive is 1%, 2%, 5%, you know, then your overall posterior odds may not be as bad as you thought. So we have a bunch of code snippets in the textbook for computing those posterior odds on the basis of prior odds, likelihood ratios, etc. These are the sections 13 and 14 and some of the practice snippets. So let's talk about different scenarios for computing using Bayesian theorem, which you encounter in practice and maybe in the exam too. So there's kind of generally 3 ways, right? Old-fashioned way is, which we don't really use it here, but if you go at old statistic textbooks, it would be a typical would be a word problem. Just like I gave you, that was a word problem. No data given. I will just say, what is the probability? What are the odds of having COVID, having tested positive for COVID? Now I have to give you some numbers. So I made up some numbers, assuming, you know, prior odds are 1 to 99, assuming true positive, assuming false positive. I have to give you all these numbers so you can use the theorem. These numbers are not derived from any data. They're just made up. That's a typical word problem from all school statistics books. So I call it a word problem. Another one is all the data is in front of you. That's more of a modern and kind of related to data science, you compute it from the data frame, directly from the raw data. That's what we are doing in active textbook. We have a bunch of data sets, and we're just doing these calculations in our data sets. Finally, the last one is we're doing it from contingency table, from aggregate data. So let's discuss how do we do the calculation from the data frame. We have a bunch of data frames in active textbook. We have Airbnb, we have movies, we have Professor Moody, synthetic data set, we have music parties and stuff like that. And examples of those odds formulations are here. So for example, what are the odds of finding a private room under $200 in Tribeca? What are the odds of PG-rated comedy achieving IMDb score 7.0? What are odds of psychology major who scored less than 90 in the class to get an A? What are the odds of a single man under 30 dying in the Titanic disaster? Notice, like you have to be very careful reading those statements, because first step you gotta do is identify the belief and identify the observation. And notice it's not always obvious, right? Let's look at the first statement. What are the odds of finding a private room under $200 in Tribeca? So which one is a belief? Which one is observation? Well, look at it carefully, right? What is observation? Observation is private room. The room is private. The belief, something which we don't know, is it costs under $200 and it's in Tribeca. Or maybe the observation is you are in Tribeca and you're looking for a private room. So anyway, this are your assumptions, and you definitely don't know how likely it is to get a price under $200. Let's look at the second statement. What are the odds of a PG-rated comedy achieving IMDb score of 7.0? Now, belief is obviously here the achieving the IMDb score, right? You don't know that. You assume it's a PG-rated comedy. So observation is PG-rated comedy. Belief is IMDb score at least 7. In the third statement, what are the odds of psychology major scored less than 90 in the class to get an A? Again, belief is simply get an A. Observation is psychology major who scored less than 90 points. And so on, right? So very important to learn what is a belief, what is observation, because everything else is a function of this. So what is a general template? I mean, the general template is both belief and observation are defined in the form of attribute equal or at least as big as a value. Both of them are defined as statements A equal or bigger than A, or B equal or bigger than B. And template is odds of A equal to A if B of equal to B is observed. Odds of content equal to R if genre is a comedy in a movies data set. Odds of a price of less than 200 if neighborhood is equal to Tribeca. So these are the examples. So odds of B equal to B if A equal to A is observed. So how do we go about it? And you can see in my snippets in the section 13 and 14, you can see a bunch of steps, which we go over. We first calculate the prior odds, we calculate true positive, we calculate false positive, we calculate likelihood ratio, and then we calculate posterior odds. So let's go at odds of P equal to B if A of equal to A is observed. So first we calculate the prior odds. So that's the number of rows in a subset of data frame with B equal to B divided by total number of rows of the data frame. So we use n row function, and that's the first step if you look at any of my snippets in section 14. Now we proceed with calculating true positive, calculating false positive, calculating likelihood ratio, and calculating posterior odds. So here is step by step what we do is we basically use n row function and different subsets, right? So true positive is the number of rows of the subset with A equal to A and B equal to B, divided by the number of rows with just B equal to B. False positive is number of rows of subset A equal to A and B not equal to B, divided by number of rows of just B not equal to B. Remember, B not equal to B is a negation of your belief. Belief is B equaling small b, and negation of belief is b not equal to b. And then we go ahead, and after these simple calculations, we divide true positive rate by false positive rate. Finally, we multiply, and we get what we wanted. We get posterior odds. So this is how we calculate. We use odds version of Bayesian theorem on a data frame, on the raw data. Yet another way, which is a little bit requires a little bit more simple manipulation, but it's very intriguing, is calculating odds from contingency table. So as you remember, contingency table is a simple table of attribute A versus attribute B. And we assume B is a belief and A is an observation as before. And we're asking, what are the odds again? We ask the same question as we asked before. Now, these odds are calculated on the basis of cells in the contingency table. And I'm not gonna go and delve into the details of those formulas. You gotta inspect them and make sure they're correct. But simply, I'll proceed with an example. So here's an example of contingency table on preferences between online teaching, in-person teaching, and hybrid teaching between arts and sciences and engineering students. So notice what is happening here. We have a body of 1,000 students. We have 500 students from arts and sciences who prefer online. 200 of our arts and sciences students prefer in-person, and 100 prefer hybrid. Engineering is far more in favor of in-person teaching, and 50, 150 is the distribution, and engineering school is smaller, of course. So we get these numbers. Now, we would like now to translate this table, and we have this function called likelihoods, which we defined in the textbook, into numbers which reflect likelihood ratios. So for every cell here in this table, we translate the cell to a likelihood ratio, which means and let me just get into this. So odds that SAS students are in favor of online teaching. So we calculated observation is SAS students, School of Arts and Sciences student, and belief is prefers online teaching. So we just do this calculation, we calculate those odds, but we put a likelihood ratio instead of the frequencies like we did in contingency table. So we go here, we do these calculations. In this particular case, it's 1.38. So now we get a different version. We can kind of call it Bayesian likelihood ratios when we have belief on the as a row name, and we have a column as the observation. So we can see that big in arts and sciences makes online 77% more likely. So that increases the odds of believing in online education. When if you're in engineering, it actually decreases your preference for online to 86%. On the other hand, for in-person teaching, 23% are more likely to believe for engineering students than for art and sciences students. I think this version of contingency tables, or a Bayesian table, is far more convincing and kind of explanatory, because you know whether the odds are increasing or decreasing. It reminds me very often the medical news which say well, if you eat vegetables, you are 50% less likely to develop colon cancer, or if you exercise, you are 25% less likely to get a heart attack. On the other hand, if you smoke, you are 80% more likely to develop lung cancer. So it's always good to know it as opposed to absolute numbers, just to know how the probabilities change. So to summarize, these are three ways to apply Bayesian theorem. One is like a word problem. I give you the numbers. You don't ask me where the numbers come from. Number two is I do it from data frame, from raw data. That's what we do in the snippets in our textbook. And finally, we do it from contingency table when we get the entire table of likelihood ratios. Remember, the most important things in odds version of Bayesian theorem is prior odds and false positives. True positive is kind of obviously important, right? But essentially, there are three values: prior odds, true positive, false positive, all what you have. All right. Thank you.